This is video 30 in the series of reinforced concrete slabs, but it will deal with columns. First, in the first part, we will talk about the failure of columns. There are three types of failure mechanisms in column. The first one is compression. When the compression stress is too high, then the concrete will be crushed. A second failure mode is due to shear. And the third one, which is the most dangerous one, is buckling. This is an example of failure by buckling. This is a typical failure because of the normal force. And this is a failure of shear force. We will concentrate on the problem of buckling. You see the problem arising with rails, for instance, when the temperature rises, then there is a compression force in the rails, and those rails can fail by buckling out, and the shape that they have can be regarded as a sinus form. Even in the lab, when you load a column with vertically, then at failure, when the buckling force is obtained, then the deformation has a shape of a sinus. Now let's take a simple reasoning, and you have a pencil loaded right on its axis, and this is a rotational axe free of friction. When this is just aligned vertically, nothing will happen, but it's unstable. The smallest displacement will rise to the collapse of this system. So that's why we create a resistance on the bottom. Then we take an intermediate situation where there is an angle theta, there is a displacement x, the normal force stays vertically, NED, and the total length of the column is L. The resisting bending moment is then K times theta, which means that the resistance is proportional to the rotational angle theta. So now we can write some equilibrium equations. The stabilizing bending moment must be bigger than the destabilizing bending moment. And the stabilizing bending moment is, of course, the spring on the bottom, K times theta. And the tangents of theta for small displacements, we are talking about very small displacements here, then x is equal to x over L. And that means that theta is equal to x over L, expressed in radians. So the destabilizing bending moment is the acting force NED times the distance x. The stabilizing bending moment must be bigger than the destabilizing, so it means that if you substitute the different values, then you will see that at equilibrium, when this is equal, then NED, we call then NED N critical at equilibrium, just equilibrium, and N critical must be K over L. So it is this factor K over L. This means that the critical force N is proportional to the stiffness and inverse proportional to the length. Proportional to the stiffness and inverse proportional to the length. We can take it a step further and use an eccentricity on the applied force, normal force. Then we do the same exercise and we see that the stabilizing bending moment is K times theta. The destabilized bending moment is now NED times X plus E, of course. and equilibrium, then at that point M stabilizing is equal to M destabilizing. We substitute the two values, we rearrange it, and then you will see that in this equation K over L, we have seen that this we called N critical. And then we can see that the displacement on top of the column is proportional to the eccentricity of the force, and the proportional factor is only depending in fact on the applied force and the critical normal force. Now let's take the idea of curvature. K, the curvature is 1 over rho, and rho is the radius. When this is, for instance, a beam in bending, and this is a very small part of the beam with an angle alpha, then you can see that K, the curvature, is 1 over rho, but 1 over rho is of course the tangents of this angle alpha, or with small angles, it's alpha. So K is equal to alpha. You just take with the elastic deformation of a concrete section. This is the section before loading, and this is the section after loading under a bending moment. You have the strain on top and the strain on the bottom. And then you see all those angles are the same. This alpha, and this alpha. X is the height, is the length of the compression height, of the depth of the compression height, and H is the total depth of the section. Then we see that alpha can be epsilon 1 divided by this portion, which is H minus X, or epsilon is epsilon of, or alpha is epsilon 2 divided by X, by this side. Or alpha is equal to the sum, epsilon 1 plus epsilon 2 divided by the total height. So you will see how, whatever you look at it, that curvature K, is equal to a strain over a distance to the neutral axis. So this is the curvature. It's 1 over rho. The curvature is a strain divided by the distance to the neutral axis. The strain is, according to the law of Hooke, the stress divided by the modulus of elasticity. We substitute, and then we know that the stress is equal to the bending moment divided by the resistance, the bending moment of resistance, W. And then W is of course the E over V. And if then you substitute in it, then you arrive at the known formula that the curvature equals the bending moment divided by the EI, the stiffness of the section. Let's look at a column. The y-axis in this direction and the x axis in this direction. It has a total length of L. It is loaded with an external force centrically N, and it has under N a deflection in the middle of the column of C1. The curvature then K is equal to the bending moment divided by EI. K, we know that this is for small deflections. K is equal to the second derivative of the elastic line, the second derivative of the dotted line here. It's A. Then we know that we can substitute it in this equation, and we will later on substitute in this equation, and we see that also the bending moment MD is always the ND times the deflection on any part of this column. It can be this one, this, or this. Now we will substitute those into the equation, and we get that the second derivative of the coordinate times Ey is plus the normal force times y is equal to 0. Now we can make a small substitution by taking a squared equal to nd over Ey over the stiffness. It must be positive. Then we have a typical differential equation of the second order, and we know for those equations that the solution is a combination of cosinus and sinus. Cosinus and sinus. So you have the solution is then a constant times sinus ax plus c2 cosinus ax. We still have two unknowns. A we know, this is this. We have still two unknowns. Y is the equation of the elastic line. Let's see if this is true. It's very simple. We just take the first derivative, then the second derivative, and then we see easily that this equals this equation, that this equation is okay. That this equation is okay. So this is the right solution, but we have two unknowns. Those two unknowns depends on the conditions. First, in the beginning, the condition when x and y is 0, it means also that the displacement is 0. So this is the first equation that we got, but it means C2 is 0. And then the second, at the other hand, when x is L and y is 0, then this condition leads to alpha L must be n times p. N is a natural number, or A equals np divided by L. That's coming from the conditions at the end. Now we have two equations for A, which is this one and this one. And now we can combine them. We have now the two equations of A. We make them equal to each other, and then we can from this equation we can calculate nd, and it has this form when now n is 1 and L is L0. It's for a model column. That means that this is simply supported. In this case, L is equal to L0, and then nd is the Euler force of a column, and can be written as the stiffness times p squared divided by L0 squared. The Euler force is then proportional to the stiffness Ey and inverse proportional to the buckling length squared.